Annyeonghaseyo. Welcome back to Automatic Control Systems lecture. In the last class, we discussed on Laplace transform. In this class, we are going to resume with the Laplace transform. In the last class, we discussed on the Laplace transform properties. In this class, we are going to apply the Laplace transform to differential equations and try to understand the inverse transform. The main focus of this lecture will be on inverse Laplace transform. So, just review the properties of Laplace transform. There are main three important properties here. One is a time differentiation, is a time integration, and the complex translation. The complex translation we discussed in the last class. So, coming to time differentiation and time integration, if you look at the differential, suppose if a function has nth order differential, what we are going to do is, when we transform this function into Laplace domain, the nth order differential will be just s power n function, and the rest of the term what you see here is because of the initial condition. The f of 0 are the initial conditions. If you remember your mathematics, when you try to solve ordinary differential equations, we need the initial conditions. The same way, when we transform a time domain function into a frequency domain or Laplace transform, we need all the initial conditions. Coming to the second property, the time integration, what we see here is that we have n differentials for the function. So, when we apply Laplace transform, n differentials convert into 1 by s power n. That means each differential corresponds to 1 by s. Alternatively, in time differentiation, each differential corresponds to s power 1. N differentials, you get s power ns. In time integration, you don't need to worry about the initial conditions. So, we have in nth differential will be just f of s by s power n. The third one is complex translation. This property we have already gone through in the last lecture. What we have is, if you have e power minus a plus or minus at of f of t, and we actually see that this will cause a shift in the s domain. You have e power minus at into f of t, that becomes f of s plus a. So, the Laplace transform with an exponential multiplication with a function will lead to a shifting in the s domain. This property is also a very important property, because this helps us to actually apply Laplace transform to wide variety of problems. Now, just for convenience, I copied the Laplace transform pairs from one of your textbook, and all the basic functions are listed here. I advise students to remember these basic functions, because these are very useful in the examination. So, when you solve any problems, you may need all these functions. You can't waste your time applying the theory and try to get the transform. They are very simple, and if you actually analyze them, it can be quite easier. So, let us go through them. So, we have an impulse function delta of t, you get 1. For a basic step function u of t, you get 1 by s. Ramp function, you get 1 by s square. In the same way, an exponential function e power minus at u of t, you get 1 by s plus alpha. So, what we are looking here is an exponential function. You have u of t just to say that this function is only valid for t greater than 0. And then you have damped ramp, sine, cosine, damped sine, damped cosine. So, all these are very useful, and I advise students to go through them and learn them. The most important thing what we are going to learn in this class is the inverse Laplace transform. If you look at the inverse Laplace transform, you have a very complex expression. Here rho 1 is the integral, is taken over a line in the region of the convergence. And if you see this function, if you have a Laplace transform function, let us say an s domain function, I want the time domain function, then we need the inverse Laplace transform. So, inverse Laplace transform, we don't use the direct application of this formula. It is very difficult to apply, but instead we try to convert the Laplace transformed function from s domain into time domain by actually rearranging the terms in the frequency domain. This is a very simple procedure and students can apply this one with ease. So what we see here is a very good example. If you follow this example, you can apply Laplace transform, inverse Laplace transform to convert any frequency domain function to time domain function. Let's have a close look. What you see here is x of s equal to s plus 8 by s into s plus 2. So this is a s domain function. What I am going to do first is to break this one into partial fractions. I think most of the students learn partial fractions in elementary school or high school. So now we are going to use our knowledge of partial fraction. So use partial fractions, break it into 4 by s. So if you actually break the function, you can actually have 4 by s minus 3 by s plus 2. Now if you look at this function, the 4 by s minus 3 by s plus 2, I can actually try to identify the direct Laplace transfer function. So first let's see here. What we know is unit step function, if you apply Laplace transform, I get 1 by s. Suppose I have exponential e power minus at u of t. If I apply Laplace transform, I get 1 by s plus a. Now in the same way, we know the Laplace transform follows additive property. So if you actually see, I can also write a x1 of t u of t plus a2 x2 of t u of t. If you apply Laplace transform, I get a1 x1 of s plus a2 x2 of s. So what I can try to do is, I can try to directly write the inverse Laplace transform from this function to directly to here. So what am I trying to do here is take this 4 by s and then we actually try to understand the relation to 1 by s and then try to write the inverse Laplace transform to u of s here. So we take this function one by one and then we can convert 4 by s first and then 3 by s plus 2 next. So by converting 4 by s and 3 by s plus 2 and directly using the inverse Laplace transform, we can directly write the solution. So this procedure is quite intuitive and we apply to all the problems. So if you follow this representation, u of t you get 1 by s, e power minus at u of t you get 1 by s plus a. So 4 by s I can directly write as 4 into u of t and 3 by s plus 2 I can write as 3 e power minus 2t u of t. This is quite intuitive and the main reason is the complex Laplace transform function, we break it into small known structures where we can directly write the time domain functions. So I am going to break a complex S domain function with the help of partial fractions into terms which are readily be transformed to time domain. By writing in the form of 4 by s minus 3 by s plus 2, I can directly write the inverse Laplace transform of 4 into u of t minus 3 e power minus 2t u of t. This procedure is how we actually solve the inverse Laplace transform problems. So for next is I want to show you how do we actually do the differentiation. Differentiation is quite easy and intuitive and you don't need to remember the complex function. We can just directly memorize in a simple way. So what you see here, let's say a differential theorem. If you have first order differential, let's say d by dt of f of t, I get s into Laplace transform f of t minus f of 0. One differential, I have one initial condition. Second order differential equation, two initial conditions. Third order differential equations, three initial conditions. So that is how the number of terms depends on the order of the differential. Now if you look at here, let's look at the second order differential. D square by dt square, we get s into d by dt into f of t or df by dt of 0. So if you expand again, what we get finally is s square f of s minus s into f of 0 minus f dash of 0. And then L, if you have a nth order differential, you have s power n f of s minus s power n minus 1 f of 0 blah blah blah. So this is quite easy and intuitive. The one thing you need to understand is how do we write for any order of the equation. So, let us have a look here. Suppose I have a third order differential of the function using a Laplace transform. If I actually write is s cube f of s, this is the first term, we get the Laplace transform, and then what follows is all the initial condition. S f dash 0 minus f double dash of 0. If you refer to the structure, this is quite intuitive. When I have a third order differential, first term s cube s power s, this s cube represents the order of this is, and all the three are initial condition. So, you see that this is s square, you write s square, sorry s cube, s square, s power 1, s power 0. So, this is quite nice. Suppose I have a fourth differential. So, then I have s power 4 f of s minus s cube f of 0 minus s square f dash of 0 minus s power 1 f double dash of 0 minus s f triple dash of 0. So, you can actually follow the structure very easily. A third order differential s cube f of s minus s square f of 0 s dash s power 1 f of f dash of 0 f double dash of 0. Then if you have a fourth order differential, you will have s power 4 f of s minus s cube f of 0 minus s square f dash of 0 minus s power 1 f of 0. So, this s power 1 is not really required, it is just for your convenience. I just wrote this number and this is not really required. So, you have minus s f triple dash. All these are the initial conditions. You see, fourth order differential equation requires 4 initial conditions. A third order differential equation will require 3 initial conditions. Based on that, we formulate the Laplace transform for differential function. So, if you look at the nth order differential, that is how you have s power n f of s minus s power n minus 1 f of 0, s power n minus 2 f dash of 0, and so on the order of the differential. Suppose if you do not have the initial conditions, differentiation is very easy. So, first differential s into f of s, second differential you get s square into f of s, third differential s power n into f of s. This is how we can actually formulate the differential. The main aspect of today's class is how do we solve ordinary differential equations with Laplace transform. So, the main purpose is solving differential equations using analytical techniques takes a lot of effort. I believe you have already solved in mathematics, Konkang-Suhak, that if you want to solve ordinary differential equations, we look for the particular solution plus the general solution and then try to compile a solution. So, the procedure is quite long and it depends on the initial conditions and also the structure of the differential equations. However, when we come to Laplace domain, we only have one method, one solution for any problem. That is the major advantage with the Laplace transform. We can solve any ordinary differential equation. It does not matter whether it has constant coefficients or different structure, we can just solve the differential equation. So, what we do is, first thing is we take the time domain equation dx by dt equal to 1. That means, if I want to solve, I want to solve for x of t, that is the main purpose. So, solving dx by dt equal to 1 means I want to solve for x of t. So, what we do is we apply Laplace transform on both the side, apply on the left hand side, on the right hand side. So, apply the Laplace transform and you see it is a differential function. So, first order differential. So, I get s into x of s minus x dash of 0 and Laplace transform of 1 is equal to 1 is like a unit step. So, of 1 will be 1 by s. So, I have this function. So, this is the frequency domain transformation for this time domain system. Now, solving for x of s, I get x of s equal to, just rearrange the terms, we get x of s equal to 1 by s square plus x of 0 minus by s. This is the solution. So, I find my x of s in the frequency domain. So, x of s is the solution of the problem, but however x of s is in Laplace domain, we need to transform back into time domain to get the solution in time domain. So, solving this one in time domain, we need the direct inverse Laplace transform. So, suppose you have this function, that means when we actually transform, we can directly transform this one. So, 1 by s square will be just over t, and x of 0 by 1 by s will be 1. So, you have t plus x of 0 minus. So, based on our learned expressions of from the table, we can readily transform the inverse Laplace, the s domain function into time domain. So, the summary of how do we solve this is use differential theorem to take Laplace transform of the differential equation, and then solve the unknown Laplace transform function, find the inverse Laplace transform. So, by using this thing, we can easily solve any problem. So, if we actually see what we have done, we apply the Laplace transform first, and then solve for x of s, rearrange the terms, bring x of s to one side, the rest of the term to other side, and then this is the solution in frequency domain. Then apply inverse Laplace transform, we get the solution. Now, let us take another simple example, quite nice example. So, we have a second order differential equation x double dot plus 3x dot plus 2 equal to 1 for t greater than 0, and now this is a second order differential equation. What we have is we have two initial conditions, what is x of 0 equal to 1 and x dash of 0 equal to minus 3. Take Laplace transform both the sides. So, first we apply Laplace transform on both the sides. So, when I apply Laplace transform, you see the first term is x double dot. So, when we apply Laplace transform, it will be x square x of s minus x of 0. So, this term corresponds to x double dot. Now, the second term is 3x dot. So, when we apply Laplace transform, I get 3 into s into x of s minus x of 0. So, this is a second order function. So, I need two initial conditions. So, I get s into x of 0 minus x dash of 0, and similarly for 3x dot. So, you have 3 into s into x of s minus x of 0, and for just x we have simple x of s. And then one Laplace transform is 1 by s, and actually it is a typo error. So, you should have here 1 by s. So, the correct expression 1 by s, please make a correction. So, now we have this function in the frequency domain. So, take the function in the frequency domain, rearrange the terms so that we can have now is x of s equal to. So, we rearrange the terms, I get a nice function x of s equal to s square plus 1 by s into s square plus 3s plus 2. So, this is the solution in frequency domain. If you want to solve this one using analytical techniques, ordinary differential equation, it takes several steps, but in Laplace transform you can solve this any differential equation in 2 steps. Now, I have the solution in frequency domain, we need to transform the system into time domain. So, how do you transform the time domain is, first we need to break the system into partial fractions, and these partial fractions are quite easy. So, what we do is we try to express the system in 3 parts, that is breaking the system into individual partial fractions. So, what you see here is the third order differential equations, and we then break it into partial fractions. So, if you remember your partial fractions from your engineering mathematics, we can write this one in a by s plus b by s plus 1 by c by s plus 2. So, I hope the students remember all the procedures to solve the partial fractions. It is very important. So, in this lecture, I have given a lot of slides on various type of partial fractions. When you have complex conjugate roots, when you have repeated roots, or when you have simple roots, it is very easy. So, all the cases I have discussed in the lecture slides. So, we have several slides in this lecture, and I am not going to discuss all the slides. I am going to only selectively discuss some slides, and all the rest of the slides are like reading materials. So, the students should go through all the slides and try to learn the partial fractions. Now, coming back to here. So, One is we have several ways to solve the partial fractions. So, we can use residual formula or we can actually use common denominator. There are several ways. So, partial fraction expanses, there are several cases. One, when you have real and distinct roots, real repeated roots, complex conjugate root, repeated complex conjugate root. So, we can have any form, we can have very simple form, several repeated roots or complex conjugate roots and even higher order. Suppose we have this function and this is a simple partial fraction, we can just break it into a by s by b by s plus 1 plus c by s plus 2. So, what we do is we take a common denominator and then we just compare the terms. So, what we do is we compare the expression on the right hand side on the left hand side. Since the denominators are the same, I can actually compare each coefficient of s power s. Coefficient of s power 2 on the left hand side is 1, on the right hand side is a plus b plus c. Coefficient of s on the left hand side is 0, on the right hand side is 3a plus 2b plus c. The same way coefficient, the numerical coefficient is 1 on the left hand side, on the right hand side is 2a. So, if you see, this is how we got the terms and that is how we actually get the term. So, we can solve these three equations, we can get the values for a, b, c. So, by this way we can solve simply any problem. Once you get the coefficients, we know the actual terms. So, now once I know a, b, c, I can actually write the nice partial fraction. And if you remember this one, this form is something very intuitive which we have already learned. 1 by s inverse Laplace transform is 1. 1 by s plus 1, you know, e power minus t. 1 by s plus 2 is e power minus 2t. So, these are the forms, if you remember, you can directly write the inverse Laplace transform. So, I just gave a formula k e power minus at, the time domain function will be k by s plus a alpha. So, by inspection, by just looking at the function and directly change into time domain, the frequency domain I can directly write in the time domain. So, x of t will be 1 by s plus 2, 1 by 2 minus 2 e power minus t plus 5 by 2 e power minus 2. So, the complex function, if we recap, the complex differential equation x double dot plus 3x dot plus 2x equal to 1, we solved with only 3 steps. So, apply the Laplace transform, do the partial fractions, and then once we solve all these steps, we directly write the inverse Laplace transform. So, once students practice a few problems, you can solve any problem within just 3-4 steps. That is the major advantage of Laplace transform. Laplace transform simplifies the ordinary differential equations procedure. So, the other problem is we can use the residual formula. The residual formula actually goes through by combining the equations and try to apply the formula a is equal to s plus a into f of s, and with s equal to substitute s equal to minus a, and then we can actually calculate. So, I leave all these problems to the students, you can directly try to solve them. Please go through them yourself. So, I have given the inverse Laplace form with repeated roots and also several other examples are also given. So, there are also nice problems with even repeated roots and also there are some problems with inverse Laplace transform with complex roots. So, since we have a limited time, we are unable to go through all these problems. So, but however, what I am going to do is I am going to discuss another one more problem to help you to understand better. So, look at this problem. I want to actually explain this problem because this is a nice system. This is a nice system which we are going to discuss in the later class as well, and I will discuss in more detail in the next class, but I am not sure if you identify what this mechanical system is. It has a spring, it has a damper, it has a mass. And suppose if this system is applied with a force F is equal to e power minus 2t, what is the displacement of the function? You will learn this modeling in the later class, the time domain. So, for the time being, we try to understand the Laplace transform. We try to model this function, we can get this nice differential equation. So, x double dot plus 2x dot plus x equal to e power minus 2at, and take the initial conditions x of 0 equal to 0, x dot of 0 equal to 1. Solving this problem is, you can understand is, when I apply a force on this body, what is the displacement profile? That means when you apply some force, what is the displacement? Just to tell you, this is suspension system in the car. Every car wheel has a spring and a damper, and this is exactly car suspension system. We will look in detail, we will discuss in detail in the next class. So, now we take this nice second order differential equation and we apply the inverse Laplace transform. Sorry, we apply the Laplace transform. Once we apply Laplace transform, I get the x double dot will result in s square x of s minus 1, and x dot will be 2 into s into x of s, and x will be x of s, and Laplace transform of e power minus 2, 2t will be 1 by s plus 2. Now, change all the terms, simplify, take x of s to one side and the rest of the other side, we get this function, and this is the solution in frequency domain. So, we have denominator terms, we have one is repeated root 1 by s plus 1 into s plus 1, the other one is s plus 2. So, we have one root that is repeating, so based on that we have the solution. So, terms with repeated roots, the partial fraction expression is written in this form, a by s plus 1 plus b by s plus 1 whole square plus c by s plus 2. The higher order terms can be found using the residual formula. Suppose when you have these repeated roots, b and c can be easily obtained, s plus 1 whole square and s plus 2, you can use the residual formula and directly get the values for bc. By using the residual formula, I get b is equal to 2 and c is equal to 1. But the rest of the roots you have to work out. Substituting these values and then equating the left hand side and the right hand side, we can get the value for a. So, by doing that, I can get the values for all the three terms. Now, I got my partial fraction. Once you get the partial fraction, the problem solved. So, the x of t will be e power minus t plus 2t e power minus t plus e power minus t. 1 by s plus 1 is e power minus t, 1 by s plus 1 whole square will be 2 into e power minus t, 1 by s plus 2 will be e power minus 2t. If we actually try to recap what we have learned in this one is, first applying the Laplace transform for the time domain function, we transform into Laplace domain. Once we transform in Laplace domain, we try to rearrange the terms, get x of s to one side and the rest of these terms to the other side. Now, the main difficult problem most of the students face is the partial fractions. These partial fractions, you need a little bit of practice and you need to understand various cases, whether the roots are real and distinct or real and repeated or complex conjugate. Look all the three conditions and see which category the roots belong, and then try to write the partial fraction expansion, find the terms. Once you find the terms, converting into time domain is very easy. So, just looking at the terms, you can directly write the expression in the time domain, and this solves the Laplace transform. So, I advise the students to actually practice a lot of problems. So, in the slides, I have given you several examples in various ways. So, what I intend to do, the reason why I give several examples is so that most of the students can have more time to solve all these problems and try to understand much better. So, because of the time limitation, I can't go through all these slides. So, I have actually covered for one type of one problem and the other one as a one. For each type, I covered one problem and one problem. So, this should help you with solving the problems in the later class. So, I think that will be the end of this week 3 part 1. In the next class, we will be actually going through the modeling of physical systems. Thank you. Kansamida.